Hi everybody, welcome to another video in linear algebra, section 6.3, orthogonal projection. We learned about orthogonal projection on the previous section. Orthogonal projection of y onto u is given by this formula and denoted y hat. Geometric interpretation. In this special case that if we have u1 and u2 orthogonal and u1 and u2, let's say in R2, in this case w is also R2 and y will be represented by this formula, and actually this is where we pick up on section 6.3. Right, now definition. Given a vector y and a subspace of w in Rn, there is a vector y hat in w such that the y hat is unique vector in w for which y minus y hat is orthogonal to w, and y hat is unique vector in w that is closest to y. So it will be easy to if we draw this out. So let's say we have the space of w, subspace w, the space Rn, and with that we have a vector y. The vector y is may or may not in the subspace of w, but y will be in Rn. Right? So let's say the y vector is not on w, and it says that there will be a vector y hat is in w. Y hat is in w, not y. So there will be a y hat in w. So y hat, this vector is in w, and that is the orthogonal projection of y onto w. So, and we say y minus y hat. So this vector is orthogonal to the subspace w. So we just have let's say when the space w is on this paper and a vector like this, and then orthogonal projection is going to be this vector, and the difference of them is orthogonal to the paper, and also the head of that vector is the closest point to the head of the original vector. So this is the closest distance from the head of the vector to the paper. Of course, if I have a random vector like this, that is not going to be the closest. If it is the orthogonal projection, that will be the closest one. Yeah, of course, if I have another vector that is also on w but it is not orthogonal projection, let's say if I have this point, if I had a random vector that is on w but not orthogonal projection, then this distance is going to be longer than y minus y hat. So pretty much the key here is y may or may not be in w, but y hat is definitely going to be on w, and y hat is orthogonal projection of y onto w, and y minus y hat on the previous section we said that is z, and z will be orthogonal to every vector in w, and z, the magnitude or the length of z, will be the distance from y to the space w. Right. Now, first example, let u1 to u5 be orthogonal basis for R5. So as you see, they are orthogonal, so they will be automatically linearly independent, and so they are 5 linearly independent in R5, therefore they will be a basis for R5. Then let y be the linear combination of these orthogonal vectors in the basis. Now consider the subspace of w equal to span of u1 and u2 only from u1 and u2. Write y as the sum of vectors u1 in w and a vector u2 that is orthogonal to w. Right. So u1 to u5 in R5, and all of them will form a basis for R5. Then if we want to write y as the sum of a vector of z1 in W and z2 that is orthogonal to W, so kind of like the scenarios here. So first of all, we have the space spanned by U1 and U2, and they are orthogonal. U1 and U2 are orthogonal. In this case, we say projection of vector y onto the space W will be equal to just projection of y onto U1 plus projection of y onto U2, because space W will have the basis of have the vectors U1 and U2, so that's what we have. And orthogonal projection we have on previous section is y dot U1 over U1 times U1 plus y dot U2 dot U2 and then U2. So this is orthogonal projection of y onto W. W has two vectors orthogonal to each other, U1 and U2, so we're just going to write like this: projection of y onto U1, projection of y onto U2, and that. And we define this as y hat. So y hat is projection of y onto W. So y hat is a projection of y onto W. And then the rest is easy. Actually, wait, they said the sum of z in W, so that could be z. That should be z. Yeah. Notation is y hat, but in this case, they want a vector in W, projection onto W, so that would definitely would be on W. So we have z1. So that will be projection of y onto W. Suddenly will be in W. And then to get to z2, we have y equal to z1 plus z2. So if we want z2, it's going to be y minus z1. So just pretty much y minus y hat is equal to z, so that we just have different name for it. Right. And then we can say vector y equal to z1 plus z2. Now, z1 is a vector in W, right? z1 is projection of y onto W, and z2 is a vector on the space that is orthogonal to W. Right. Yeah. And that apparently what we have in the theorem here. Let W a subspace of Rn, then each y in Rn can be written uniquely in the form of y equal to y hat plus z. Y hat is in W and z in W perpendicular. In fact, U1 to UP is any orthogonal basis of W, then we have that. So the key here is the U1 and U2 in this case, or U1 and UP in this case, have to be orthogonal to each other, and that because orthogonal they will be linearly independent and therefore will be basis of W. In that case, we can say projection of y onto U1, projection of y onto U2 on the way to projection of y onto UP. Linear combination of all of that gives us the projection. So this is projection of y onto W. And then we have the projection from y onto W, and subtract y by that projection, we have this vector which is orthogonal to W. Right. Let's look at our first example here. Let U1 be 2, 5, and negative 1, and U2 negative 2, 1, 1, and y is 1, 2, 3. Observe that u1 and u2 is an orthogonal basis for w spanned by u1 and u2. Of course, we can check real quick if we just do the dot product of u1 and u2. So let's say u1 dot u2 so that is negative 4, 5, and negative 1, and plus negative 1. That equal to 0. Because the dot product equal to 0, which means u1 is orthogonal to u2. So we do have orthogonal basis for w. In that case, we will write y as the sum of a vector in w and a vector that is orthogonal to w. So first we will write y hat, which is projection of y onto w is projection of y onto u1 and projection of y onto u2. Projection of y onto u1 is going to be equal to y dot u1 over u1 dot u1 u1 y u2 u2. Right. Now we just do the math here. Y is 1, 2, 3. U1, 2, 5, and negative 1. U1 dot U1. And then U1. Y. U2. U2. Right, so we just do that. And so we have 2. I'm just going to say 2 plus 10 minus 3 over 4 plus 25 plus 1. Negative 2, 1 times negative 2, 2 times 1 plus 3, and then at bottom negative 2 times negative 2 is 4, 1 times 1 is 1, 1 times 1 is 1. So that gives us 12 minus 3. So that is 9 over 30. So 3 over 10. And that is 3 over 6. That's 1/2. So, yeah, so that gives us So just keep that over 10, so 6 over 10, 15 over 10, and negative 3 over 10, plus negative 2 over 2, that's silly, so it's just negative 1, and then 1/2 and 1/2. Right, just subtract them. So this is 6 over 10 minus 1, so 0.6 minus 1. So we can, if we write that as a fraction, that's negative 0.4. That is 1.5 plus 1/2, that will be 2. And then negative 3 over 10, negative 0.3 plus 0.5, that's 0.2. If we have fraction, or if we don't want fraction, I mean if we have decimal, if we don't want decimal, that will be negative 2/5, 2 and 1/5. Of course, we can just put all of this in the calculator. We use the list. All right, 3 over 10 or 0.3 times the list of 2, 5, and negative 1 plus 0.5 times the list of negative 2, 1, and 1. Right, to fraction. Right, so that's what we have. So this vector y hat, projection of y onto W. So this vector is in W. Now we just need to find a vector that is orthogonal to W, which definitely is not on W. So this is first one we have. Next we will find Z is equal to Y minus Y hat. That gives us Y is 1, 2, 3 minus Y hat is this. So we end up with 1 minus that the plus, so that 1 and 2/5, that's 7/5, 1.4 if you will. 2 minus 2, that's 0, and 3 minus 1/5, so 15/5 minus 1/5, that's 14/5. Of course, the way we can just say we have the vector 1, 2, 3. Subtract the last result we have, second answer. And yeah, so that's what we have. And this vector is in the space of perpendicular to W. So we decomposed y into two vectors. One of them is in W and one of them is orthogonal to W. So we say y equal to the vector of y hat plus z. Y hat is negative 2/5, 2 and 1/5, then plus 7/5, 0 and 14/5. So this vector in W, this is in the vector that is orthogonal to W. Right. So that's simple enough. Just find the orthogonal projection of y onto all the bases, onto all the vector in the bases, and then just add them up. That will give us projection of y onto W, and then we subtract it from y, give us the vector on the space orthogonal to W. Right. Of course, that's what we find the orthogonal projection of a vector onto a space, knowing the orthogonal basis of that space. Now, so the orthogonal projection of y onto orthogonal projection of y hat of y onto W is a sum of projection of y onto one-dimensional subspace that are orthogonal to each other. So that's exactly what I just said. Now, so the calculation is pretty much just that. Now, what we can get from that is we can find the closest point, because we know how to find the projection of y onto W now. But that orthogonal projection has a lot of meaning. First of all, that will give us the closest point from y to W. And if we want to find the distance, we just need to find the length of z, or the length of y minus y hat. And that's essentially what we have here. Let W be a subspace of Rn, let y be any vector in Rn. Then y hat will be the orthogonal projection of y onto W, and y hat is the closest point. In W to y, in the sense that y minus y hat is less than or equal to y minus v, for v is any vector in W. So we mentioned earlier, here we have the vector v randomly on W, and that distance to y is going to be longer, or at least equal to y to W. Yeah. So once again, if we have a point randomly on the head of the vector, orthogonal projection will give us the closest point to it. Any other vector distance will no longer be the shortest distance. The shortest distance is where it is orthogonal projection. Right, now let u1 be 2, 5, and negative 1, u2 be negative 2, 1, and 1, and y is 1, 2, 3. And W is spanned by those. Find the closest point of y to W. Actually, this is exactly the example that we have earlier, because I don't want to do this calculation again. So now find the closest point in y to W. So I will say this, the closest point in W to y is the point y hat, which is projection of y onto W. And from previous example, we have the point y hat is equal to the calculation y hat is going to be negative 2/5, 2 and 1/5. Negative 2/5, 2 and 1/5. Yeah. So we seem already done the calculation. That's what we have. So the closest point in W to y is the y hat projection of y onto W. Of course, if the point y, if the vector y is in W, then the projection will be itself, and the distance between them would be 0. Like earlier we said, if we have a vector that is not on the plane, but in some case that vector could be on the plane, in that case the projection of the vector onto the space W will be itself, and the distance between them two, between the vector to the space W will be 0. Right, so simple enough. Next we have this example. The distance from point y in Rn to a subspace W is defined by the distance of y to the nearest point W. Find the distance from y to W, where this is y, this is u1, u2. Right, so when we say the distance from y to the nearest point in W, what is that? What is the nearest point in W to y? Of course, that is y hat, right? So we say distance from y to the nearest point in W. That means we're going to find the distance between y and y hat, which is the same thing as the norm of y minus y hat, which is pretty much the length of y minus y hat is going to be z. Yeah, so they be given in different form. But instead of say the distance, find the norm z, the proper description will be the distance from y to the nearest point in w. So once again, y is a vector not on w, and the orthogonal projection, in that case the distance between them is going to be given by this vector. This vector would be z. Yeah, this one, this vector is going to be z. Right, now pretty much we just find z and then find the length of z. Right, so simple enough. First we'll find the y hat, the closest point in w to y, and the point in w that is closest to y, which is y hat. So we say closest point, so the point in w that is closest to y is y hat, which is orthogonal projection of y onto w. So we have y hat equal to projection of y onto w will be projection of y onto all the bases of w that are orthogonal. The important thing is the vector have to be orthogonal, so make sure that vector orthogonal. So I multiply u1 and u2. The dot product should be equal to 0. If the dot product is not equal to 0, we cannot use this theorem. Just to make sure that the vector in the basis must be orthogonal. So be 5 minus 2, that minus 2 times 2 minus 4, and minus 1. 1 times minus 1, so that's 0. Yeah, so the vector are orthogonal to each other. Good. So that's why we can use the theorem. Say the y hat is the projection of y onto u1 plus projection of y onto u2, because the vector u1 and u2 are orthogonal to each other, so we certainly can use that. Y u1 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 u1. Right, y 1 to negative 2, 1 to negative 1, u1. Right, once again, y negative 1, negative 1, negative 5, and 10. Sorry, this is y. And u1 5, negative 2, and 1, 5, negative 2, and 1, then y u2 1 2 negative 1, right? So negative 5, negative 1 times 5, negative 5 times negative 2, that's plus 10, and plus another 10. And here we have 5 times 5, so it'll be 25 plus 4 plus 1. Yeah, we calculate all of that first, give us a fraction, and then just multiply by the vector. And then multiply this, give us a fraction times the vector. Negative 1 times 1, negative 5 times 2, and 10 times negative 1. 1 times 1 is 1, 2 times 2 is 4. And that gives us 1, 2, negative 1. Right, so 10 and 10, 20 minus 5, 15 over 20, 15 over 20, that's 1/2. And now negative 10, negative 1, that's negative 21. Negative 21 divided by 6, 21 divided by 6, 2 and 3 cancel, that's 7/2. Yeah, 21 over 6. Yeah, I'm just going to write down. Right, I'm just going to enter this. That is 15 over 30, that's 1/2. 5, negative 2, and 1, minus, this is just, I just want to write 21 over 6 times the vector 1, 2, negative 1. Right. We have negative 1, negative 8, and 4. Right, so that is y hat, which is the point in W that is closest to y. And so the distance, so we said the distance from y to W is equal to the distance from y to y hat. Because distance from y to W is the distance from y to the closest point to W, and that equal to y minus y hat. So the point y is negative 1, negative 5, and 10. Subtract y hat, negative 1, negative 8, and 4. So I just type negative 1, comma, negative 5, and 10. Subtract y hat, which is this point. Second answer, that will do 036. And so, of course, the norm of that vector is easy, equal to Pythagorean theorem 0 square plus 3 square plus 6 square. Sorry, kind of for now space here. Right, 0, 3, and 6. So the norm of that vector is 0 square plus 3 square plus 6 square under square root. 6 square 36, 3 square is 9, square root of 45. Which is square root of 9 and square 9 times 5, which is 3 square root of 5. So simple enough, right? So the orthogonal projection is the point that is closest to y but on W, and if we want to find the distance, just subtract y to the closest point on W. Right. Now, here's a very nice result. If we have U1 to UP is an orthonormal basis. So what is different between orthonormal and orthogonal? This has to be, of course it's going to be orthogonal, but it have to be normalized as well, meaning that all the vectors have to have the length of 1. So that is different than what we have earlier. Earlier we have is orthogonal basis. This is orthonormal basis of W. In that case, when we put all of those vectors together, we have the vector, we have the matrix U. If this is the square matrix, that could be orthogonal matrix, so kind of confusing, right? We have orthonormal basis, but when we stack together, that gives us a matrix. If this is a square matrix, that will be orthogonal, not orthonormal. Yeah, of course we'll get back to that later. But for now, if we have orthonormal basis for W, and we stack all of that in the matrix, so to find the projection of Y onto W, we just find the matrix U times U transpose times Y for Y in Rn. So once again, orthonormal basis, we have two properties. That is orthogonal, of course. And the second part is normal. Normal means that the length of each vector is 1. So we say U1, U2, and so on must be equal to 1. So each vector is a unit vector, and they are orthogonal to each other. Right. Now to see if this formula works, we just take a look at this example. By the way, this is exactly what we did on the first example. Of course, the problem will be the same as the first example, U1, U2, and Y. Right. Use that fact to compute projection of W onto Y. We're going to use this. In this example. Right. Of course, we can always use this calculation, but in this case, just want to utilize the result here. So first, we have U1 and U2. So with simple check, we say U1 dot U2, and we already did that. It is equal to 0. So we have U1 is orthogonal to U2. So they have one part of it orthogonal. Now we just need to reduce that to the unit vector. Right. This is bad if we have the same. Right. So here what we do. We have the vector 2, 5, and negative 1, right? Right. So we have to turn this, let's just say normal line. The vector U1. So we, meaning that we have U1 divided by the magnitude of U1, or the length of U1. So that gives us orthonormal. Right, U1, 2, 5, and negative 1, and the length 2, 5, and negative 1. Right, 2, 5, and negative 1, and then we have square root of 2 square, 5 square, and negative 1 square. Of course, that 4, 25, and 1, that's 30, square root of 30. So we have that is square root of 30, so I just say 2 over square root of 30, 5 over square root of 30, and negative 1 over square root of 30. So that is normalized version of u1. Now we normalize u2. So u2 over the magnitude of u2. So negative 2, 1 and 1. Negative 2, 1 and 1. And we have square root of negative 2 square, 1 square and 1 square. So that is 4, 1, 1, that's 6, negative 2 divided by square root of 6, 1 over square root of 6, and 1 over square root of 6. It looks complicated now, but it should turn out nicely. So we have the normalize of u1 and u2. So it is normal and it is orthogonal, so together orthonormal. So the vector, the matrix U will be equal to, I'm just going to put the vectors here in column. Yeah, it looks complicated with the square root and all, but like I said, it will, in a calculation, it will turn out a lot better than, it should not have any square root in our calculation at the end. So that is U. This is the matrix of matrix whose columns are orthonormal basis for W. Right, so orthonormal. Right, next, the projection of Y onto W. If we know U, it's going to be U times U transpose times Y. Yeah, that's exactly what we have, so we can say Y hat right. So this is U. And then U transpose, so I just turn this sideways, column become a row. And what we have is multiplied by the vector Y, which is 1, 2, and 3. right? Let's multiply this matrix first because a bunch of square root when to multiply together, it should cancel out. And 3 rows, 2 columns, so it's going to be a 3 by 3. Right. 2 over square root of 30 times 2 over square root of 30, that is 4 over 30 row times column minus 4 over 6, that minus times minus will be 4 over 6. Right, that's the first one. Next, that will be 10 over 30 minus 2 over 6 and minus 2 over 30 and minus 2 over 6. Ten over 30, I will pick it up now, minus 2 over 6, 25 over 30, plus 1 over 6, minus 5 over 30, plus 1 over 6, minus 2 over 30, minus 2 over 6. As you say, there's no square root after this. Minus 5 over 30, sorry, plus 1 over 6, and 1 over 30 plus 1 over 6 times 1 to 3. Right. Actually, we can just put this in the calculator. Right. A matrix. 3 rows, 2 columns. Right. 2 over square root of 30 over square root of 6, 5 over square root of 30, (1 over square root of 6), negative 1 over square root of 6, and 1 over square root of 6. Right. Of course, I could then multiply with, I could enter this again. However, those are the transpose of each other, so all we need is just one of them, right? So that's all we need, really. That's going to be u. When we hit enter, don't mind about that, just that matrix. Of course, do not change this to fraction because we cannot. With the square root, I cannot go back to fraction. However, what we do is we're going to take second answer should be that matrix. We just enter times the matrix again, but this time second matrix transpose, right? Because they are just transpose of each other, so we just say the matrix times the matrix transpose. And now just turn into this, and let's see if there's fraction. Right. Let's see back. Right. As you see, I enter it wrong. Let's be 30 here. Alright, so once again, the matrix times the matrix transpose. Right. Fraction for fifth 0, negative 2/5, 0, 1, 0, negative 2/5, 0, 1/5 times 1, 2, 3. So actually we're just going to say it. The last answer, which is this matrix, times the matrix of 3 row 1 column, 1, 2, 3, and we have negative 2/5, 2, and 1/5. Now if we compare to the answer we have on the previous, for the first example we have in this video, u1, u2, and y. Y hat, the projection of y onto w is going to be negative 2/5, 2, and 1/5. Negative 2/5, 2, and 1/5. So they should be the same. So this is another type of calculation. You said, well, that sounds like a lot of work. But in terms of calculation, if we have to program for something with a bunch of matrix, with a bunch of vectors, doing this by hand, it's not as efficient as just enter in the matrix in this form. Right. So once again, there's two ways to compute projection of y onto w. Knowing all the orthogonal basis of w, of course one way is doing that. Or we turn all the vectors into the normalized version. So we have u, and projection is just u times u transpose times y. And of course we should get the same thing. And that's all I want to cover in section 6.3. Thank you for watching, and see you in another video in linear algebra.